Today we're going to be talking about 8.4, which is experimental and theoretical probability. So let's talk about what that means. So theoretical probability is a probability determined on the basis of reasoning. If you flip a fair coin, the coin will land on either heads or tails. Therefore, we can reason that the theoretical probability of landing on either heads or tails is 1/2. So the idea here with theoretical probability is what we've been calculating thus far. So you know how we've been doing calculations on probability? All we've been doing is what we call theoretical probability, okay? Now, experimental probability is the probability determined on the basis of results of an experiment repeated many times. So experimental probability is based on like a trial that you might do. If you flip a fair coin 10 times, the experimental probability of landing on heads can result in any of 11 probabilities. Never landing on heads, always landing on heads, or any number in between. So theoretical probability, which we've been calculating in all of the other lessons, is the number of favorable outcomes over the number of possible outcomes. And experimental is the number of times an event occurs over the number of times the experiment is done. So for number 1, it says determine the theoretical probability of rolling a fair 6-sided die and landing on a 3. So how many sides are there to a die? 6. Good. So the chances of landing on a 3 are? 1 in 6. Very good. Now the next one says a fair 6-sided die is rolled 100 times, of which it lands on 3 a total of 20 times. Determine the experimental probability of landing on a 3. So how many times did we actually land on what we wanted? 20. Out of how many trials? 100. So this is our experimental probability, which reduces to 1 over what? 5. So as you can see, the theoretical probability is 1/6, but sometimes the experimental will be higher or lower than that because it is experimental. Now looking at number 3, determine the theoretical probability of picking a heart from a deck of 52 cards. How many hearts are there in the deck? 13. There's 13 of each suit. 13. Yeah, that's what I was thinking. Yeah, 13 times 4 is 52. So this reduces to 1/4. So a heart makes up 1/4 of the deck. Each suit does.
Mr. Russell, do you know how to count cards? I feel like you do.
I don't know. Maybe.
How many Vegas casinos are you banned from?
I've never been to Vegas, but I've been to a decent amount of casinos.
You working your way up to the big leagues?
Yeah, if only. I bet like $5 maybe. So 12 times the card is randomly drawn and placed back into a deck of 52 playing cards. On 4 occasions a heart was drawn. Determine the experimental probability of drawing a heart. So, how many times did we actually draw a heart?
4.
Out of how many trials?
12.
Good. So the experimental probability is what?
4 and 12.
Which is 1 over 3. So your experiment came out with an experimental probability of 1/3, which is higher than the expected, which does happen. It's not exact. Theoretical is exactly as it says it's theoretical. So now we're going to try another problem using planets. So of our solar system's 8 planets, in order from least to greatest distance from the sun, we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. You randomly draw one of these names from the planets, basically you draw one of the planet's names, and you write a report on that planet. What is the theoretical probability of selecting a planet whose distance from the sun is less than Earth's? So how many planets have a distance to the sun less than Earth's? 2. We have Mercury and Venus, which are closer to the sun than Earth. So 2 out of the total number of planets, which is 8, which means we have a theoretical probability of 1/4. After receiving complaints, a skateboard manufacturer inspects 1,000 skateboards at random. The manufacturer finds 992 skateboards have no defect. Selecting a skateboard at random, what is the probability that it has no defect and the probability that it does have one? So let's do no defect first. So what's the chance of no defect? What out of what? Good, 992 out of 1,000, right? That's the chances of no defect, which comes out to be 99.2% certainty. So basically 99.2% of the skateboards that they produce based on 1,000, trialing 1,000, come out with no defect. And then how many of them come out with the defect?
0.8.
Good. 8 out of 1,000, which is also 0.8%. So this is one of these scenarios. I just want to mention this. This is not like necessarily, it's connected to the lesson, but for every type of experiment that is done, if you go into like more in-depth statistics, there's a certain sample size that's required to get a general good idea of what the scenario is. If you only like tested out 5 skateboards, you probably wouldn't get one with a defect, right? So it's not really a good what we call sample size for actually accurately representing the data. So you have to keep in mind that the sample size has to be a certain size in order for the data to be more accurate. Does that make sense? So you have to have a larger sample size to get more accurate data. So the next one says, you randomly ask 500 households in your town if they have a dog. Of the 500, 197 respond that they do. If your town has 24,800 households, about how many households are likely to have a dog? So what you'll often see is you'll see a sample experiment conducted to get a general experimental probability amount, which you can then apply to estimate other values for other larger scale things. So how many people out of the 500 have a dog? Good, so 197 out of 500. And you can convert this into a percentage. So basically, based on the study, the people they sampled, 39.4% of those people have a dog, right?
Yeah.
How can we use this information to estimate how many of these people have a dog, the whole town? Yeah, we can take the percent of it, right? So if I have a class of 20 and you want to take 50% of that, that's 10, right? So the way we do that is we take the number of people and we take 39.4% of that. Now to do that mathematically, we convert our percent into a decimal and multiply. So you move the decimal place 2 times to the left. Basically before you multiply it by 100. And you should get approximately 9,771 likely have dogs. Now, why didn't I just say that this many people have dogs? Why did I say likely have dogs?
Because it's not you can't be for sure. It's just
You can't have 1 or 2 of a dog.
Well, that's true.
well, it's
So
like estimating.
it's estimating, yeah. It's using the probability. It's using the experiment to apply it to a larger set to see if it's accurate. So that's the whole lesson today. Like I said, it's pretty straightforward.